Hello everyone, in this video I'd like to discuss how can we implement the low-pass filter function by using just one equation, either ladder logic or SCL structure test logic in your PLC or in any computer or embedded system. The typical application while we are using the low-pass filter, for example, if you are using your PLC or any computer system using ADC to read the analog signal. For example, this is our PLC system, and if we are using the analog signal, the typical analog signal, for example, maybe the pressure or the temperature or float. Very typical analog signals in industry, especially for the process automation system. However, you will find in the real system, all those signals, for example, this is the curve of the signal change. You will see following those signals, there are a lot of analog noise come with those signals. And those analog noise will cause the confuse for your PID, for your closed loop system. Ideally, if your signal change could be a very smooth line, then that can give a very clear feedback to your closed loop system, okay, to your closed loop system. Right? So this is the feedback, this is the analog feedback using the sensor system, right? If we are using the PID. Get rid of the noise sometimes can improve your control quality. Then how to program a low pass filter into the system, right? Typically the noise is a high frequency, come with your required signal, right? Using the program to run as filter function, traditional way, we could do this. For example, if we are using the analog to pick up, this is the K, the current time. If we are picking an analog signal, that is temperature. Okay, I will name the temp here. And the current time, that temperature is 35 Celsius degree. And the previous time is K minus 1. And maybe that is a 35. Then the time based on this, the previous time, this is the K minus 2, okay? But maybe the temperature was 35.5. A very conventional way to do the filter function, this is the average calculation. Basically, we can pick the K minus 1, K minus 2, then average them together. So we will plus them together. And then average, this is a 3, so over 3. Then we will get an average signal, right? However, if your signal has a very strong noise and you need to summary more values together, for example, if you are going to pick 20 values, then you need to summary 20 values from K minus 1, K minus 2, then go to K minus 19, right? Then you need to summary 20 values, summary them together, and then over 20, and then you get an average value, right? And the more annoying thing is we move to the next cycle. That means the K minus 2 need to be get rid of that. Then this one will change to K minus 1. This one will change to K minus 2. And you will get a new K here. That means your buffer, this is the 3 values in a buffer, and this is the 20 values in this 20 variables buffer. Then that means you need to program something to shift your buffer. Basically, the idea is FI, FO, first come, first out. Then you need to shift your buffer, keep shifting this buffer, and then you need to summary this buffer together and over the numbers of the data in this buffer. So typically, calculate this one average, you need to do the FIFO and the summary and the calculation. And this is the one average. And if your system has 100 analog, you need to do this average. You can think about, you need to shift this typically using the for loop, right? And you also need to calculate this and over this 20. And sometimes do the derive is not good. In case you forget this denominator, accidentally your denominator is equal to 0 at the initial status, then your system will be stopped because your system doesn't happy while this calculation derive a 0 at there. So this is a potential issue there. Then I will introduce a very simple way to do this low-pass filter. Before we do that, let's recall a typically analog low-pass filter, what that looks like. Okay, this is one typical analog circuit. So this is a resistor, and this is a capacitor, and this is a ground. Okay, and this is the output, V out, and this is the load, ground. Okay, and this is the resistor R and the capacitor C. So the output voltage here and the input voltage here, let's write down the transfer function of this circuit. Out over voltage input, right, equal to 1 over SC and SC plus the R. Okay, and this equal to what? This equal to, if we times SC both numerator and denominator, then this equation change to 1 plus the SRC. Then let's recall, so when we talk about the first order transfer function, so let's grab this. So if we compare with this first order transfer function, let's think about this. If we over RC at denominator and denominator, then this equation will become to 1 over RC, 1 over RC. Then you will see this area, this is basically, this is the A, right? And this area, this is the A. Then you will see, okay, so this equation actually equal to AS plus A and times K. So K equal to 1 because this is a low-pass filter, right? The output need to follow the input, so the gain is 1. And A become to the 1 over RC. So typically, this low-pass filter transfer function is a typical first-order transfer function. Then leverage the knowledge we introduced from the previous videos. Once we know those values, using the first order transfer function and the difference equation to implement this low pass filter, right? Then let me introduce, so what does mean of this, right? This area looks very important, right? So a typical low pass filter transfer function, the style is like this. This is a low pass filter transfer function. And here, omega c cutoff frequency. And this omega c, this unit, that's the rate per second. Take care. It is not hertz. It's a rate per second. Okay, so this is the cutoff frequency. Then maybe some people will ask, so what does mean of the cutoff frequency? If I'm using the Bode plot, okay, this is the amplitude. The unit is dB. So the cutoff frequency, for this case, this is the 1K hertz. So 1K hertz at this spot here, this is the -3 dB. So this is the cutoff frequency. But in this case here, this unit is a rate per s. So we need to convert into the hertz. If our PLC is reading a temperature signal, if we are going to design a low-pass filter, the cutoff frequency is 0.2 hertz. Then we convert this 0.2 hertz to rate per second. This convert, we can use any very easy calculation tool to convert this. For example, we can go to this website or any tools convert from hertz to rate per second. For example, if this case is a frequency is 0.2 hertz, calculate. Then the calculation result equal to 1.25. Okay, in this case, I will write down 1.25. Okay, here I will write down its converting result is 1.25 rate per second. That means this transfer function, this low pass filter transfer function is equal to 1.25 s plus 1.25. If you recall, using the knowledge we learned from the previous video, that means here as a low pass filter, as a first order transfer function, there a equal to 1.25. Okay, using the knowledge I introduced before, this equation is a difference equation converted from the first order transfer function. Okay, and in this case, k equal to 1, or basically we get rid of the k here because k equal to 1. And how can we calculate this area? Okay, then we will see E power area is A TS. So again, A here equal to 1.25 and the TS equal to what? TS, we can define this. So in this case, because my analog changed very slow, if I assume if I'm going to use the 100 milliseconds as my equation, this equation calculation time, 100 milliseconds as an equation calculation time, then that means this is 0.1 second. Take care, this unit is second. Then this area equal to E minus 1.25 times 0.1. Okay, so TS, this is the sample time. Then let's calculate what the result of this. Okay, so firstly we can type in E equal to 2.718, and its power area is equal to minus 0.125. So 0.125 and a minus. Okay, let's do this calculation. And it's equal to 0.88. Okay, so it's equal to 0.88. Then we will see what that looks like now for this equation. This area equal to 0.12. And this area change to 0.88. Then if I write down here, so if we have one signal times y k minus 1 and plus the input 0.12, then this is our input. So this equation become very simple now. And take care, if you recall, based on this equation, so take care, our TS time is 0.1 second. And this cutoff frequency, this is 0.2 Hertz. Okay, so the important thing is how can we define this square, this area, this is this area. How can we calculate this? So typically this value here equal to 0.9 to 0.7. This value, and this area is just 1 minus 0.9 and 0.7. Okay, so we will program this equation here into the PLC, and let's see the result. And in this case, I will use an analog channel and use the Siemens PLC 1200 PLC with a RTD, a temperature sensor, and we will see with or without this equation what the analog input will be. And we can compare this averaged value. In this case, I'm using Siemens 1200 PLC, and this PLC comes with 2 analog channels. So if we go to the properties of this CPU, and it has 2 analog channels, I'm using the channel 0, and this address IW64. I took off the smoothing function, so we can compare the analog signal with or without the filter, and we will see the difference. And because this channel, this is the IW64, then I'm using this way the normal X and doing the normalized calculation, and then using this scale S convert to a real value. So this typically convert my RTD sensor and the transmitter and convert this RTD temperature sensor signal into a temperature signal. This is the converted temperature variable. Then I will program the filter equation we just introduced. So firstly, I will create a OB, the cyclic interrupt, as I introduced. In this case, the sample time of that equation, this is the 100 milliseconds here. Okay. And we can select the ladder logic, okay, and click OK. Then I will create another function, okay, okay. So we can call this function named filter. Okay. And I can use the structure test, or actually the ladder logic also works. You will see that equation is very simple. The structure test or SCL can show that equation clearly. So I will use the SCL. Okay, and I will create a DB. So we can call this DB filter. Create a DB filter. And here we can name analog input. So here I can name that input temperature. Okay, and this is the real, and output, this is the average of temperature. Average of the temperature. And also we need to record the temperature from the previous cycle time. Okay, so we can name that average temperature K minus 1. And then to set a value for this square, this area actually comes from this calculation. For example, in this case, I'm going to set this area directly to 0.88. And the right side here, this is 1 minus this area, 0.88. So we can call this area, we can name as the factor, filter factor. Okay, then let's go back. Okay, I can name this filter factor. Then let's program this. Firstly, I will go back to this FC filter. We can firstly set this factor filter, set as 0.88. This is my temperature case. Okay, then the average temperature value that equal to this factor multiply this average temperature from the previous cycle time, okay, and then plus there's one bracket, 1 minus 1.0 minus this area, this factor, then multiply the input temperature. This is the temperature signal before the filter. Okay, that's it. So we can see how simple of this equation. Then where of this value came from. So this temperature input, this temperature signal equal to, if we go to here, my temperature signal, this value. So I can drag this to here. Okay, my temperature signal. This is the analog signal before the filter, and this is the after the filter. After filter, we'll see this average temperature signal. It is here. And we can set this factor signal. Okay, then we can return this. And I can write down here, this area actually comes from the exponential and minus that omega c multiply the sample time. Okay, the sample time. Okay, came from this. Don't forget. So this temperature K minus 1 came from the previous sample time. So how to program this? So this one actually equal to just below this equation. This K minus 1 value came from here. So every time we calculate this equation, we will move the current average value to here, record that. And then when the next time the CPU call this function, calculate this equation, then this K minus 1 come from here. Prepare for the next cycle. Okay? So don't forget this one here. This record the average value for the next cycle program here. Okay? And then another thing very important, don't forget, we created this is interrupt code. This is the 100 milliseconds interrupt code. Again, let's go check these properties. This cyclic interrupt, this is the 100 milliseconds. Very important because this is 0.88 that calculated by this 100 milliseconds, 0.1 second came from this. So this whole equation need to be called by 100 milliseconds. So how can we call this? Go to the cyclic interrupt and call this FC filter. Call here. Okay, so then everything complete. So we can download the program and we can monitor the temperature signal and the average temperature signal. Okay, we download the program and then let's firstly go to the AI RTD and let's firstly monitor this conversion signal, and we can see my ambient temperature now is 26 Celsius degree, 26.4. And then let's go to the FC filter, and this FC filter, this is the equation calculation here, and as we can see now, this is the average signal, and we can see this average signal is very stable here. This average signal, this is the average temperature value here. Okay, so if I go to the watch table before I turn on the trace, and if we go monitor, this one is directly sensor signal, and this one is the average signal. So we will see this average signal change just a little bit, but this directly signal, it changed a lot. Okay, now if we go to the trace, so we configured these two signals, and now let's download the configuration and let's monitor. In the meantime, I can drop this RTD, the sensor, into the water and change the temperature a little bit. Let's see the signal before the filter and after the filter, what their difference. So as we can see here, this is the red is sensor before the filter, but the blue is after the filter. We will see the significant difference, right? So it has the noise signal come with this temperature sensor signal, and this blue is super smooth, right? So it's increasing. Now I will drop it into a cold water, and we will see the temperature will be changed, will decrease. Okay, and you will see it always comes with some noise come from this red, but the blue is smooth. And unit, they are the same for both curve. Okay, apparently this filter is working. And again, currently this filter, this cutoff frequency is 0.2 Hertz. It's basically low if you are using the pressure or flow. Keep in mind the parameter of the cutoff frequency. This value will not be the same. You better manually calculate this, or you can use the program calculate this. That time you can basically set the cutoff frequency, either the Hertz or the rate per second. Then you can calculate a result for this filter factor. So basically the calculation will be this area. You have the 0.1, 100 milliseconds sample time. This cutoff frequency comes from this area. But in this case, I'm going to use this very simple way. So you will see the key portion is this, the filter factor. And this area is a 1 minus filter factor. This is the only we need to set for this calculation is this 0.88, this value. Okay? And we can see this is very easy. And now if we go back to the trace, we'll see the red always comes with some noise, but the blue comes from the filter. It runs smoothly. Then let's do a quickly summary. This is low pass filter transfer function. This low pass filter transfer function is the same as the first order transfer function when the k equal to 1. Then borrow the knowledge we derived from the previous videos using this equation, this difference equation here. Then this equation will become this very simple style. This area is a constant value according to your setting. The omega c comes from your cutoff frequency. Take care, in the transfer function, the cutoff frequency, the unit is a rate per second. So you need to convert the frequency into the rate per second. Okay? And then this area, once you got this area equal to 1 minus this area. And typically from my experience, if you are going to average a slow response signal, typically this area equal to 0.9 to 0.7. Then this area will be 0.1 to 0.3. This area must be 1 minus this. Okay? Then this YK is your averaged value. This is the low pass filter by using this equation, this difference equation method. Alright, this is how can we use the first order knowledge and implement this low pass filter transfer function by using this difference equation this way. Thank you for watching.
Thank you for watching. If you like this video, please give me a thumb up. If you like to watch more videos in my channel, please subscribe and hit the bell. Thank you for watching.